Hello, Physical Geography Lab. This will hopefully be a quick video overview of the Earth-Sun Relationships Lab, which looks just like what you have here. Remember that it can be found linked on our Canvas page. Go to Modules, and it will be in Modules as you have found the other ones. So you just look for the right name. And so I'm not going to open that up. I'm going to go straight to the lab itself. And as always, this little video is not a replacement for reading word for word carefully, sometimes rereading and pondering the text and the examples in the lab activity itself. And remember, your job is to take this, if you're working in Google Docs and Google Drive, which I recommend, to make a copy so that you can then put in your own information. The key thing here is we're going to take a look at how Earth's journey around the sun causes seasons. You should have covered this in physical geography lecture at some point. The very, very short version is that it's all about how high the sun gets in the sky on any given day. That I call that angles, the maximum sun angle, and how many hours and minutes the sun spends out during that day. I shorten it as hours and angles, hours and angles. Hours of sunshine per day, angles of sun in the sky. So the very short version is, as hours and angles increase, we get more energy. That leads to heating. That causes summer. As hours and angles decrease, we get less energy from the sun. That leads to cooling, and that causes winter. Now, this is probably an oversimplification, but it's a really good oversimplification. So the first thing is, I want you to review this summary chart. This should be stuff that is somewhat familiar from physical geography. And in particular, one of the most important things to consider is this issue of declination. What is declination? It's the latitude of the vertical ray where the sun is directly over your head. That's a 90-degree sun angle. Sun is directly overhead. That never happens, by the way, in Sacramento, but you may have traveled somewhere in the world where this happens. So the declination changes during the course of the year. The latitude where the sun is passing directly overhead changes during the course of the year. And you can see a little summary here. I put it both using compass directions and also using positive and negative numbers. So in the December solstice, it's at 23.5 south, latitude called the Tropic of Capricorn. Then in March, it crosses the equator. Then in June, it's at 23.5 north, a latitude called the Tropic of Cancer. And then it goes back and crosses the equator. So I want you to review all of these dates and all of this information, but you're going to use that chart. You're also going to use this map to basically explain kind of what I just explained. I want to make sure as we introduce this lab that you understand the sun's changing declination during the course of the year. And so I have presented the information in map form. You can see these latitudes. So if we start here, you can see the sun is directly above, directly overhead, the Tropic of Cancer at 23.5 north on June 21st. This is the June solstice. Then what does it do? It moves southward and it crosses the equator on September 21st, the September equinox. Then it keeps moving southward, day after day, week after week, until it hits the Tropic of Capricorn, 23.5 south latitude. That's the December solstice. Then what does it do? It turns right back around day after day, week after week, and it marches back northward. So that is really what I have asked you here, is to put that into your own words. I want to make sure you understand how the declination changes as Earth revolves around the sun during the course of the year. And again, what's the big deal about declination? Well, that's where the sun is directly overhead. That's the location that's getting the most energy. So then we start to walk through these issues one by one. I know this looks like a lot of pages, but there's a lot of maps and tables and graphics. So the very first thing we do is we jump into looking at hours of sunlight at different latitudes and different times of year. So these are just different representative latitudes. These are different times of year. And I have given you approximately how many hours per day the sun is out at these locations, at these latitudes, on these days of the year. You then go down and answer the questions below. The first one says complete the grid. So you do the math. Okay, I've tried to explain it as straightforwardly as I can. What is a range? You take the highest minus the lowest. What is a mean? You take a group of numbers and you add them up and you divide by the number of numbers. So I have tried to walk you through this, but I want to see you do the simple math here. I'll give you a little hint. This trips some people up. What about the annual range for this square right there? How do I get the annual range? Well, highest minus lowest of these numbers. So what's the highest? Clearly 24. What's the lowest? 0. 24 minus 0 is what? 24 would go there. So I'm going to let you do the rest of them. Read every single word carefully, ponder this. You are easily supposed to spend 3 hours on this, which is what a normal, at least 3 hours or up to 3 hours. That's what a normal lab would take. So then you read every question as carefully as possible. I'm not going to read all of them, but it's going to ask you about the ranges. It's going to ask you about the means. It's going to ask you about what that means for that location. What if on average you have lots of hours of sunshine per day? What does that mean for your location compared to other locations? I imagine it means you're going to get more energy. Okay, so again, read the questions carefully. Then we take a little detour to make sure you can use a technical resource to determine declination. I gave you a chart that told you declination at 4 different times of year, but you can figure it out any day you want for any day of the year. Earth has a declination. And so I send you to this website. Here's a little sample of it. I'm going to go there in a second. And basically I ask you for these 5 dates, please tell me what the declination is. You can answer in north, south, or positive, negative numbers, but be incredibly clear. I'll take a date that's not here. Let's say August 1st, okay? So what do? Well, you go to this NOAA solar calculator. And it looks like this. We're not going to use the map. You can go through it and figure out. It's very powerful. It's got a lot of capability. For the moment, we're just using some limited capability. We're not going to use the map, but we're going to use the date here, and then you're going to read the declination. That is what is referred to in this graphic right here. So you're really only going to use the date and the declination at the moment. What did I say? I believe I said August 1st. So this is just an example. 1st of August, okay? And once you click that, it automatically changes the declination. This is a latitude. This is the latitude on Earth where the sun is directly overhead. And we're not going to get into specifics of the exact time and minute. We could get super exact, and we're not going to. And it doesn't matter what location we're talking about, because right now we're just talking about the Earth's declination on that day. So what is this? 17.77 degrees. And please notice it's a positive number. This website uses positive and negative numbers. In August, the declination is still north of the equator. If I switched it over, for instance, to let's say October 1st, okay, what do we have? We now have a negative number. So this is in degrees. This is the number I'm looking for. You need to report it in the proper format. This would happen to be 3.56 degrees south, or negative 3.56 degrees. The previous one, when we were in August, was what? 17.77 degrees north. Why north? Because this is clearly a positive number. So you simply use that calculator to answer these questions. And it says use this symbol. And again, if you want to use the negative and positive numbers, do that, but do it accurately. If you want to convert it to north or south latitude, then do that. It needs to be crystal clear when I grade this. So then moving right along, why do I need to give you a resource to figure out the declination? Because you should be able to, on any date of the year for any location in the world, tell me how high the sun's going to get in the sky. That's an important figure. That's an important piece of information to determine how much energy we're going to get from the sun. Remember, hours and angles, hours and angles. So section 4 is all about calculating a maximum sun angle for any date and any location. So the short version is you can figure out the maximum sun angle if you simply take 90 minus the difference. The difference between what? Well, wherever the sun is hitting and where your location is. If you know where the sun is hitting, that's the location that's getting the 90-degree angle. If you know how far away you are from that location, you just subtract that from 90. Now I'm going to stop sharing for a second, and I'm going to try to use the globe here to demonstrate this. Okay, so I often, and I'm going to forget the tilt for a second, but I often use Lake Victoria in Africa. Okay, so let's say we're in a boat in Lake Victoria, right here. The sun is directly overhead at that moment, solar noon. Well, what's my sun angle? 90 degrees directly overhead. But for everybody in the world, is that the case? No. What if I'm 10 degrees north of there? Okay, so here, let's say the sun is hitting here. This is the declination. It must be an equinox. And I'm in a boat. My sun angle at solar noon, when the sun reaches its highest point, is 90 degrees. If I'm 10 degrees away from there, at 10 degrees north, let's say, my sun angle is what? 10 degrees less than 90. 90 minus 10 is 80. So the whole key to this is simply comparing where the sun is overhead to where the location is. If you can take the difference, subtract the difference from 90, there's your maximum sun angle for that day. So let me go back to sharing. So yeah, 90 minus the difference. Well, I have created a grid that completely walks you through these bits of information. So what do? I give you two examples and completed them for you. I give you a location and a date, location and a date. So I give you the first two, you need to review these, how the format is, and you need to do the next four. So, and I walk you through it. First one says, use Google to figure out the latitude. You already did that in one of the last labs. And make this easy on yourself. It clearly says round off to the nearest full degree. Please make this easy on yourself. So 39 north. And then it says use the NOAA solar calculator, which is what you just did, to determine the declination. Round to the nearest full degree, 11 south. Then calculate the difference. And this is where you got to pay attention. How do I figure out how many total degrees between these two locations? Well, when they're in different hemispheres, this latitude is way up in the northern hemisphere. This latitude is down in the southern hemisphere. You add those two numbers and you get a difference of 50. In this case, San Diego on May 25th, here's the latitude of San Diego, here's the declination for May 25th. The difference in degrees between those two is not very much because we subtract. They're in the same hemisphere. So if they're in different hemispheres, add. If they're in the same hemisphere, subtract. That rule is explained right up here. So 33 minus 21 is 12. Then what did I say? How do you calculate your maximum sun angle? 90 minus the difference. 90 minus the difference, which is what these two examples show. So what do we know? In October 22nd in Sacramento, the sun's only going to get to about 40 degrees in the sky. For May 25th in San Diego, the sun is going to be 78 degrees in the sky, much higher. So you're going to complete the rest of these following the directions. And then I give you an entire grid of maximum sun angles at different locations and different times of year. This matches what you saw before. So you can tell how high the sun gets in the sky. Look at the equator. Those are some of the highest numbers on the grid. Okay, the sun gets high in the sky at the equator. Look here at the Arctic Circle. Those are some low numbers. Look at the North Pole. Those are really low numbers compared to the rest of the grid. So you're going to, again, calculate the ranges and the means following the directions. And this time I only made you complete a few of them. And then you're going to answer questions. And then as we move on, hours and angles do what? They determine how much energy you get. So section 6 has you look at the amount of energy received, and I skipped making you interpret this fairly complex graph, and I just put the data in for you. But this is in watts per square meter as a measurement of energy. How much do these locations get at different times of year? And so you can see some places get nothing. I wonder why a place would have absolutely no energy coming in. Maybe there's no sun in the sky. So you look at these numbers. You take the ranges and the means. You fill in only the grid squares that I left empty, and you go and you answer the question. I want you to know you're going to see a question like this at this point for the third time. It's okay. I want to reinforce that concept. And then it asks you things like, look at your ranges. How do they change from the equator toward the pole? So like for this one right here, okay, if we go to the ranges and we start at the equator, as I go toward the, as I go toward the North Pole, how do they change? If I start at the equator and I go toward the South Pole, how do the ranges change? Do they go up? Do they go down? That's what I want you to recognize. Pretty simple stuff. So you read every question in complete detail. And yeah, this is maybe a little bit long, involves some reading. This should not be beyond anybody's capability. So I wish you the best of luck. Again, do not hesitate to contact me, but get started, take this seriously, and the due date is in Canvas. All right, thanks.